Hello and welcome in this lesson about numerical sequences. I'm Mohamed Kadem Kare. You may download the PDF of this lesson on the website I indicate here. It will be also indicated in the description below the video on YouTube. The outline of the lesson will be firstly to define sequences and give their basic properties. After that, I will present arithmetic sequences and then geometric sequences. The fourth part of the lesson concerns the limits of sequences. And finally, I will present the induction principle. So let's begin by defining sequences and giving their basic properties. A sequence is indeed a list of real numbers. Here is an example. We shall denote by U1 the first term, U2 the second term, and U3 the third term. And we say that U1 is the first term of the sequence. More generally, we shall denote by UN the nth term of the sequence, and we call n the index. So UN will be said to be the term of the sequence of index n. In some cases, the sequence will start from some UP for some given number p. We then say that UP is the first term of the sequence, and we denote the sequence by UN for n larger or equal than p. We will see now that a sequence may be seen as a function. Remind the notation of the set of natural numbers n, which comprises the numbers 0, 1, 2, etc. We denote also the set of reals or real numbers by R, and it comprises all numbers such as these ones. Okay? So remind that a function is a mapping which goes from the set of real numbers to itself, and it gives to each real number x an image denoted by f of x. By analogy, a sequence may be seen as a function from the set of natural numbers to the set of real numbers, and to each index n it associates an image denoted by u index n. So we may denote also the nth term of the sequence as u of n. So this is a notation which is equivalent to this one. It is more often this notation which is used for sequences. Here is an example of a sequence defined explicitly. We give the value of un as 2 multiplied by n plus 3. And this is the more simple way to define a sequence, to give the expression of un as function of n. Sometimes sequences are defined recursively. This means that we are giving the first term of the sequence and then how to calculate un plus 1 from un. Think, for example, of a ladder where when you were a child, you learned to climb the first step, then how to move from one step to the other. In this case, you can climb the whole ladder. Here's an example. We are giving the first term of the sequence, which is this one, and then we are given also the relation between un and un plus 1, which is this relation. So if they ask us how to calculate u1, it will be 5 multiplied by u0, which is 2, and this gives the value 10. We can also calculate u2 by the same rule here, 5 multiplied by u1, which gives 50. We now present increasing and decreasing sequences. A sequence is called increasing if un plus 1 is larger or equal than un. Here is an example. This is the n-axis, and this is un. If I take, for example, 3 values here, this sequence is increasing. It is called strictly increasing if the inequality is strict. On the other hand, un is called decreasing if un plus 1 is smaller or equal than un. Here is an example of decreasing sequence. And un is called strictly decreasing if the inequality is strict. Finally, a sequence is called monotonous if it is increasing or decreasing. In order to study whether a sequence is increasing or not, we may study the sign of un plus 1 minus un. Consider, for example, the sequence un given by this expression. If we calculate the difference between un plus 1 and un, we find the value 3, which is strictly positive. So this sequence is strictly increasing. We present now bounded sequences. A sequence is called bounded above if there exists a constant k such that un is smaller or equal than k for any n. This is an example of bounded sequence. Imagine that it takes some values here, okay, but it never exceeds some value k. This sequence is bounded above by this value k. On the other hand, a sequence is called bounded below if there exists a constant m such that un is larger than m for any n. This is an example of sequence which is bounded below. Okay, imagine that it doesn't go below this value m. So this sequence is bounded below by the value m. Finally, a sequence is called bounded if there exist two constants m and k such that un is between m and k for any n. Okay, now we will present two types of sequences called arithmetic sequence and geometric sequence. Consider firstly arithmetic sequences. An arithmetic sequence verifies un plus 1 equals un plus r, where r is called the common difference of the sequence. You may think of a ladder here, where u0 is the ground level, and then r is the difference between two successive steps here. Imagine that there are many steps in the ladder, and we designate by un the height of the nth step. So un is this value here, this is the nth step. With this analogy, we may see that un equals u0 plus n multiplied by r. You may also verify that un equals up, if this is the value u underscore p. So you see that un equals up plus n minus p multiplied by r. So try to remember these formulae because they are very useful in exercises. I will present now formulae for the sum of terms of an arithmetic sequence. To this end, I present a first formula which gives the sum of the first n integers. It says that 1 plus 2 plus n equals n by n plus 1 divided by 2. The proof of this formula is as follows. Let's denote S, the desired sum. We can write S in the other side by beginning with n, then n minus 1, and finally 1. If we add these two terms, we see that here we get n plus 1, but also here we have n plus 1, etc., until the last term, which is also n plus 1. So you see that 2 multiplied by s equals n plus 1 n times, which is n by n plus 1. So if we divide by 2, we see that s equals n by n plus 1 divided by 2, which is the desired formula. This formula permits to prove more general results. Indeed, for any arithmetic sequence, the sum u0 plus u1 plus un equals n plus 1 multiplied by u0 plus un divided by 2. And we will remind this formula in the following terms. In fact, the sum of the terms of an arithmetic sequence equals the number of terms here, which is n plus 1 in this case, multiplied by the first term plus the last term divided by 2. And this way of expressing this formula permits to see that up plus 1 plus un equals the number of terms, which is n minus p plus 1 in this case, multiplied by the first term, which is up, plus the last one, which is un divided by 2. Observe and remind that the number of terms between p and n equals n minus p plus 1. Don't forget this plus 1 for this number of terms. Okay, so you see that this formula permits to get the sum of number of terms for any arithmetic sequence beginning with an arbitrary index p and ending with an arbitrary index n. The proof of this formula is given here. I will not give all the details to prove that the sum of the terms of an arithmetic sequence is given by this last formula. You may make pause in the video or get the PDF of the course from my website, and you can check that these steps are good and we get the desired formula. We present now geometric sequences. We begin by an example. Assume that the price of your smartphone is divided by a factor 2 each year. Let u0 be the starting price and un be the price in the nth year. Then we have the relation that the price at year n plus 1 is 0.5 multiplied by the price at year n. More generally, a geometric sequence verifies un plus 1 equals q multiplied by un for any n, where q is called common ratio of the sequence. Obviously, applying this formula, we may get that u1 equals q multiplied by u0, and also u2 equals q multiplied by u1, which equals q squared multiplied by u0. More generally, we have that un equals qn multiplied by u0, and un equals q to the power n minus p multiplied by up. these formulae are very useful in exercises, so try to remember them. We shall now give formulae for the sum of terms of a geometric sequence. But as for arithmetic sequences, we begin by first simple formula. Indeed, here we need the sum of the first n powers, 1 plus qn, which is equal to this expression here. In order to build this formula, it is enough to multiply 1 minus q by this term here, and this product will be made in the following way. We firstly multiply these terms by 1, which gives this value here. Then we multiply this term by minus q, which gives the second line here. But now observe that q here and minus q disappear, q squared minus q squared, etc. until the last term, and the remaining terms are 1 and q to the power n plus 1. Now divided by 1 minus q, we get the stated result. Using this result, we may establish that for any geometric sequence, the sum of u0 plus u1 plus un equals the first term u0 multiplied by 1 minus q to the power n plus 1 divided by 1 minus q. And we shall retain and remember this formula in the following form. We get the first term here multiplied by 1 minus q to the power number of terms, n plus 1 here is the number of terms in this example, divided by 1 minus q. And indeed this formula is very general, since if we add up plus 1 plus un, we get the first term, which is the up here, multiplied by 1 minus q to the number of terms, which is in this case n minus p plus 1, divided by 1 minus q, where q is the common ratio of the sequence. Let's now define and give the basic properties of the limits of sequences. Before giving the definition, let's give some intuitions. We want to define the fact that the sequence un tends towards L when n tends towards infinity, which is denoted the limit when n goes to infinity of un equals L. Indeed, this means that any interval of the form L minus A, L plus A contains all the terms un whose index n exceeds a certain value k. In other words, for any A, strictly positive, there exists a certain integer k such that for any n larger than k, un falls within the interval L minus A, L plus A. So this may be written mathematically like this. For any A, there exists an integer k such that n larger than k implies un is within the interval L minus A, L plus A. We now give the mathematical definition. So we say that the limit of un equals a real number L if for any A there exists an integer k such that n larger than k implies un is within the interval L minus A, L plus A. And in this case, the sequence is said to be convergent. Okay? On the other hand, we say that the limit of un equals plus infinity if, so the same conditions, whatever is the value of A, there exists some k such that now n larger than k implies that un is within the interval A plus infinity. So observe the difference here. For a finite real number L, the interval is in this form, whereas for the infinite case, the interval is in this form. Finally, we say that the limit is minus infinity if, under the same conditions, when n is larger than k, un is within the interval now minus infinity minus a. So according to the type of limit you have, you consider different types of intervals here. We give now some examples. The limit of 1 over n when n goes to infinity equals 0. So this is the first example. You have to remind this result. The limit of n squared when n goes to infinity is plus infinity. And finally, the limit of minus 3n when n goes to infinity equals minus infinity. Here is a remark which is important in some statements and some exercises. A non-convergent sequence is said to be divergent. Okay, so a divergent sequence means that either it has plus infinity or minus infinity as limit, or it has no limit. On the contrary, a convergent sequence means that the sequence has a limit, and this limit is a real number, so it is finite. Here is an important property of the limits of sequences. We can do the sum, the product, or the ratio of the limits as long as there is no ambiguity. For example, the limit as n goes to infinity of n multiplied by n squared plus 1. So here we have plus infinity. Here also we have plus infinity. When we add 1, we get also plus infinity. And when we multiply plus infinity by itself, we get also plus infinity. But in some cases, we have an indeterminate form, such as infinity divided by infinity, or 0 divided by 0, or 0 multiplied by infinity, or plus infinity plus minus infinity. In this case, it is necessary to transform the expression to remove the indeterminacy. Here is an example. Consider the ratio here. So we get that this term goes to infinity, and also the denominator goes to plus infinity. So here we have an indeterminate form. In order to transform this expression, we take n here as a factor, and the remaining terms are 1 plus 4 divided by n, and also in the other side we get n outside the expression, and we get n multiplied by 1 plus 2 divided by n. So you see that the n now disappear, and we get this remaining ratio, and as n becomes large, this ratio goes to 1. So you see that we get the final result by some work on the expression. Observe that when un is defined explicitly as function of n, then we treat the limit of the sequence as the limit of the associated function. Formally, if un is some function of n, and if the limit of f of x as x goes to infinity equals L, then the limit of un also equals to L. Here is an example. If un is given by this expression, then the limit as n goes to infinity of un equals 3, since this term here, 1 divided by n, or 1 divided by x, goes to 0 as x goes to infinity. We state now a useful theorem. Assume that un plus 1 equals some function of un, where f is a continuous function. So if the limit of un goes, as n goes to infinity equals L, then in this case L equals f of L. Let's see together how it works. So un goes to L, so this term converges to L. Then all this term, since f is continuous, goes to f of L. And also the left hand side here converges to L. So L equals f of L. And in this case, we try to solve this equation to get the value of the limit L. Let's give an example. Assume that u0 equals 5 and un plus 1 equals the square root of un. If the limit of un equals L exists, then necessarily L equals the square root of L. Hence, L equals 0 or 1. Indeed, from this equation, you can we can deduce that L squared equals L. Then you get this term in the left side of the equality to get that L squared minus L equals 0. So L multiplied by L minus 1 equals 0, and hence L equals 0 or 1. So this is a way to get the limit when you have that un plus 1 is a continuous function of un. In order to get the limit of the geometric sequence, you need the following result. The limit of q to the power n equals 0 when q is between -1 and 1. And it equals plus infinity when q is larger strictly than 1. And finally, this limit does not exist if q is smaller than -1. So as an application, since here q is smaller than 1, and it is between, in fact, 0 and 1, so we are in this case, the limit of 1/3 to the power n equals 0. On the contrary, since 2 is larger than 1, then the limit of 2 to the power n equals plus infinity. Another example, the limit of -1 to the power n does not exist. Indeed, when n is even, this power equals 1, and when n is odd, this power equals -1. So this sequence goes from -1 to 1 all the time, so it does not converge to any limit. Now, since un for a geometric sequence equals u0 multiplied by q to the power n, so the limit of un as n goes to infinity equals u0 multiplied by the limit of q to the power n, which is given by this result here. We now state an important theorem called sandwich theorem. It says that if a sequence un is between two other sequences v and w, such that the sequence vn converges to some real number L, and W also converges to L, then in this case, the in-between sequence U necessarily converges to the same limit L. This is the final result of this theorem. So this is when the limit L is a real number. Another case is when U is larger than some sequence V which goes to plus infinity, then the sequence U also goes to plus infinity. And this is obvious, since if this sequence becomes very large, and U is larger than V, then necessarily U also becomes very large. The third part of this theorem is that if U is smaller than a sequence W, such that W goes to minus infinity, then U also goes to minus infinity. And here also, this is obvious, since if W goes to minus infinity and U is smaller than W, so necessarily U also goes to minus infinity. Here's an example. If U is between these two sequences here, so let's see, when n goes large, this term converges to 2. The right-hand side also converges to the same limit 2. So u also converges to the value 2. We now state a theorem about the limit of monotone bounded sequences. The first result says that an increasing and bounded above sequence admits a finite limit. So this is an example. Assume that we have an increasing sequence, but assume also that it is bounded above by some value, say k. In this case, the sequence converges to some limit which is finite. Also, a decreasing and bounded below sequence converges to some finite limit also. We have also two other useful results: an increasing and unbounded above sequence. So assume that we have an increasing sequence, but it is never bounded by some value. Then in this case, this sequence goes to plus infinity. We have also the last result here, that a decreasing and unbounded below sequence tends to minus infinity. So these are the four possible results of monotone sequences and their limits. The last part of this lesson concerns the induction principle. So we want to prove some property P of n. For example, we want to prove that 1 plus 2 plus n equals n multiplied by n plus 1 divided by 2. So this is our property P of n. And we want to prove this property for any n larger or equal than 1. Then we proceed in 3 steps. The first step, called initialization, we show that P of 1 is true. Indeed, P of 1 is equivalent to 1 equals 1 times 1 plus 1 divided by 2. And this property is obviously true. Then we show in the second step what is called inheritance. We assume that P of n is true for some n and show P of n plus 1. Indeed, if we consider the left-hand side for the property P of n plus 1, it equals this sum. So the first n terms sum to this value since P of n is true. And then we should add the last term, which is n plus 1. So if we factorize by n plus 1, we get this expression here, and this shows that P of n plus 1 holds true. So as a conclusion, the property P of n holds true for any n larger than 1. The induction principle may be stated in the form of a theorem called the induction principle theorem. It may be stated as follows. Let P of n be some property if P of 0 is true, and if P of n implies P of n plus 1, then the property P of n holds true whatever is n larger or equal than 0. Again, we can make the analogy with climbing the steps of a ladder. If you can climb the first step of a ladder, and if from each step you can climb the following one or the next one, then as a conclusion you can climb the whole ladder. Finally, let's observe that sometimes we want to show the property Pn for all n larger or equal than some k, which may be 3, 4, or whatever you want. Then in this case, the initialization step consists in showing P of k is true. This is the end of the lesson. See you later. Goodbye.